Welcome to Mathematics with Tom. I am Tom, and today we are going to find the Laplace transform of cosine omega t and the Laplace transform of sine omega t. Well, I want to just write this out for a moment. Remember that the Laplace transform of some function of cosine, we'll just start with that, cosine of omega t, this would be the integral from 0 to infinity of e to the minus st cosine of omega t dt. And that will work. You'll have to integrate by parts twice if I'm not mistaken, which I don't really want to do. But notice this. Notice that I could have also said that the Laplace transform of cosine omega t would be the same thing as the real part of the integral from 0 to infinity of e to the minus st e I omega t dt. Because remember, we know that e to the I omega t by Euler's identity is cosine omega t plus I sine omega t. But wait a minute, that means that we could do this. Think about this. If I wanted the Laplace transform of sine of omega t, that would come from the imaginary component of the integral from 0 to infinity of e to the minus st e I omega t dt. Oh, do you see what we can do? We can take the integral of e to the minus st e to the I omega t once and for all. The real component will give us the Laplace transform for cosine omega t, and the imaginary component will give us the Laplace transform for sine omega t. This seems kind of like a home run option. So here we go. We're going to find both of them at once by solving. I'm just going to call it capital I for integral, and the integral is going to be from 0 to infinity of e to the minus st e I omega t dt. All right, start out by adding our exponents. This is the integral from 0 to infinity of e to the minus, this is going to be an s minus I omega t dt, and then we can evaluate that. This is going to give us, so capital I, our integral is now equal to, or now we can just multiply. So we're going to have a minus 1 over s minus I omega e to the minus s minus I omega t evaluated from 0 to infinity. Now, the integral seems kind of strange, but I'm going to show you how these limits aren't so difficult. If we think of it this way, minus 1 over s minus I omega times, I'm going to write this in two parts. One of these parts is e to the minus st. The other part is e to the I omega t, evaluated from 0 to infinity. Well, when I do that, notice that the e I omega t is sines and cosines, and those are going to oscillate. But e to the minus st, as t gets very large, goes to 0. So I can just say that this becomes minus 1 over s minus I omega times 0. And then at 0, e to the minus st, that becomes 1. E I omega t at 0, that becomes 1. So minus 1. And there we have it. Our I is minus 1 over s minus I, plus 1 over s minus I omega. Now, this, we still aren't done, because remember, we need the real part and we need the imaginary part. So we need to multiply by its complex conjugate. In other words, divide the complex number. So s plus I omega over s plus I omega. this is going to give me s plus I omega over s squared minus omega, plus omega squared. And then now look at what we've got. Now we've got s over s squared plus omega squared plus I times omega over s squared plus omega squared. So we can say that the real part of our integral I, that is, that we already said what that was. We said that's the Laplace transform of the cosine of omega t, and from just this line above we also found out that that is s over s squared plus omega squared. And what else can we do? And, well, we can look at the imaginary component. The imaginary component of this integral. Well, we said that that is the Laplace transform of the sine of omega t. But from the two lines above, we can see that the imaginary component is just omega over s squared plus omega squared. Remember, when we're taking the imaginary part, we're just taking the coefficient with the I. We don't include the I in the imaginary part. I hope that helps, and thanks for watching.